In 1 year, it'll have collected more data than the whole of optical astronomy so far, from Galileo onwards. Almost all telescopes have been made with aiming to zero in on something really little and look at it in great detail. In recent years, people have got more interested in surveys, collecting big populations of similar sort of objects. The idea behind the Rubin Observatory is to take in a huge amount of sky with a very large telescope, so it collects a lot of light, so it can see things that are very distant and very dim. It'll take a 30-second exposure, close the shutter, move to another part of the sky, take another one, and it'll do that all night long. It's a very intense way of doing astronomy. It's going to discover something like 10 times more objects in our own solar system than we know about already. New asteroids, objects in the outer solar system, so many galaxies, billions and billions of them. It might discover Planet 9, which is proposed planet in the very far outer reaches of the solar system that no one's been able to see yet. You're getting this sort of snapshot of the entire southern sky out to a very great distance, back halfway through the history of the universe every few nights. And it builds up over the 10 years of the project into a sort of time-lapse movie of the universe. It needs a lot of infrastructure to keep that going smoothly. Vera Rubin Observatory is in central Chile. It's a 2-hour drive from La Serena up to the observatories. That site was chosen because the air is very dry and it's very stable. The sky is exceptionally clear. It looks quite futuristic and different from other observatories. It has this strange sort of flowing architecture that comes down the side of the very peak of the mountain so that the prevailing wind sort of flows smoothly over the building. You go in at ground level and immediately go upstairs. They have the control room of the telescope, which looks a bit like something you would have for a space mission. They have this enormous display on the wall when it's operating, which has 24 graphs showing the sort of temperatures and pressures and heat flows at various places, because there are objects in there that generate heat. There's potential for that heat to damage the sensors. A lot of things that they're now doing manually, they will learn how it's done, and then they'll teach an AI system to do them.
You can imagine the observing specialist more like an airline pilot. If things are going well, 90% of our night will be very smooth, but there's that 1 to 10% of time that you really want us there.
They have what's called the scheduler, and this is the brain of the telescope. So it knows what the survey needs, essentially making all these decisions minute by minute on where to point the telescope to get the maximum amount of data. Then we went up through the clean room where everything is put together.
So we actually had the telescope distributed in pieces across the entire observatory, all talking to each other. But it was very like Frankenstein's monster.
In pieces, yeah. I mean, this is a real luxury, isn't it? Having this amount of space to sort of work on the parts of the telescope.
You'd be surprised at how quickly it fills up. Level 3 is now basically a warehouse for our coding chamber.
That's the device they have for recoating the mirror. Every so often, they have to take it out of the telescope, strip that off because it's become degraded, and recoat it. I went through into the base of the telescope.
So this is the great octopus in the sky, although there's quite a bit more than 8 arms. All of these fiber cables, electrical conduits, insulated refrigerant lines, they have to rotate with the telescope.
Of course, right.
Up from there, I entered the dome itself where the telescope is. It fills the room much more than other telescopes I've seen.
It is so short and squat, isn't it?
It's big and fat, and I love it.
When we saw it in motion, it was extraordinary. Firstly, it was so smooth. The whole thing sits on a thin layer of oil between 2 flat surfaces. This is an enormous machine weighing 350 tons. And when it turns around, it's silent. Eventually, it'll be moving at 4 or 5 times the speed we saw it moving.
So when we change positions from the telescope pointing from one part of the sky to the other, We want it to be able to move as quickly as possible, and once it's there, take the highest quality image as possible.
On a normal telescope, it's quite hard to get accurate images right at the edge of your field of view. The images are often a bit distorted, but by having 3 mirrors, you can lessen that effect. It's a very unusual mirror with essentially 2 mirrors in the same piece of glass. It has an outer ring, which is the first mirror that the light hits, and the light is reflected there to a second mirror, which is curved outwards, and that reflects it back towards the center of the main mirror before it enters the camera. A lot of the science they want to do depends critically on accurate shapes of things that you're looking at.
So this is the only telescope that I think has a 3-mirror, 3-lens design.
The camera for Vera Rubin is the largest camera for astronomy that's ever been made. So it weighs 3 tons. It's about the size of a small car. The sensor array is this big array of CCDs. CCDs are the little camera chips. This has 189 of them, and they're big. So it's a huge amount of data in each image. The width of the image is 7 full moons across, and so the whole image is about 40 full moons. It scans the whole sky, visible from the mountaintop in Chile. Every time Vera Rubin Observatory takes an image, the data is read off all these chips in about less than 3 seconds, and then it's immediately sent down an optical fiber to La Serena, and then again immediately off to the United States and ends up at SLAC laboratory in California. First thing they do is tidy up the image so that essentially all that scientists will see are astronomical objects that they want to see. There will be something like 10 million alerts every night. The next thing they do is they compare that image to the same image taken 3 days earlier. It could be as many as 10,000 things have changed in that image, and they send out a stream of alerts to astronomers around the world. They could be a new supernova, or it could be 2 neutron stars colliding with each other. A neutron star is what's left when a very large star ends its life, can't burn anymore, and it sort of collapses. Occasionally you'll get 2 of them that are orbiting each other, and they will gradually orbit closer and closer together and then merge. In 2017, gravitational wave detectors sensed one and sent out an alert. Telescopes took ages trying to find it, about 11 hours. People are hoping that if we get another alert like that, Rubin can be diverted. Its wide mirror will be able to pick up enough light to find it much quicker. There are all sorts of really fascinating objects that are very rarely seen. We're hoping we'll see many more of them. Many scientists think there aren't enough other telescopes to follow up all the things that Vera Rubin is going to find. Apart from the idea of finding fast-moving things, the other type of data that it's going to produce is just a complete catalogue of the universe. Images will become more and more detailed and precise as it collects more light. Our knowledge of how galaxies evolve is all based on the biggest, brightest ones that have been around for a long time. To understand how galaxies work, we need to know this much larger population of dwarf galaxies. Rubin is going to find vast numbers of these things that at the moment we just can't see. They probably aren't just smaller versions of the big ones. They're irregular and lumpy and not a sort of fully formed shape. As it collects more photons during the course of the 10 years, one of the main targets is trying to understand dark energy, this mysterious force that is making the universe not just expand, but getting faster. The shape of a galaxy's image can be distorted because other matter in front of it acts as a lens, distorting the path of light. If you have a large number of them, you can do statistical comparisons, and they'll be able to do very, very precise measurements of how this clumpiness has changed and what that means for the accelerating expansion of the universe. All the while that they've been building it, space has been getting more and more crowded. Satellites can leave massive trails across images, and because Vera Rubin is looking at such a large part of the sky, it's really hard to avoid them. Right now, The trails from the satellites affect 1% of all the sky area that they cover. By the end of the survey, they may have much less usable data than they do at the beginning. The people that are studying the solar system, they think they're going to start seeing things in the first year, whereas looking for the very subtle effects of dark energy, it may not be towards the end of the survey. Almost every area of astronomy will use it in some way. They want it to work relentlessly for 10 years, so they're still doing a lot of preparation to make sure they're ready for that enormous cinematic production that they're going to start towards the end of the year or early next year.